Good morning. I am José Antonio. I'm director of this Institute of Mathematics, and I am very, very happy and very honored to welcome you to this 7th ARTA. It is a big honor for us to have you here. As you know, representation theory has a long tradition in Mexico. It started, I guess, in the early 70s with Raimundo Bautista, and then Roberto Martinez, and then some other very, very good mathematicians. And then there came a very brilliant, by the time very young mathematician. Now he's still young in spirit, José Antonio de la Peña. And I'm very happy to know that this conference is in celebration of his 60th birthday anniversary. And I just want to say that we are very happy, very pleased to have you here. We hope you will have a great meeting. And I thank you for being here. And I leave you with the speakers to start.
Okay, so just let me greet you all. Welcome to this ARTA 7, and thanks to all of you for coming. Some of you with quite some obstacles, and yeah, some of them still on their way. So, but anyway, let's begin. And here we start with.
Okay. Okay. Good morning, everyone. I am glad to see a lot of known people. Well, first I would like to say congratulations for your birthday, José Antonio. And now we will have the first talk in this morning by Helmut Lenzing, working with José Antonio. Please.
First, a check-up of the microphone. Yes, it seems to work. So, thank you very much for the invitation to present a talk about this eminent mathematician, José Antonio. But first, we will have a look back for 30 years. Here you see José Antonio. The two pictures you see in the center and in the right hand are made in our garden. I will specify the date a little later. The picture in the left-hand corner where you see José Antonio discussing with Peter Drexler was made 3 years later. So these central pictures were made in 1989 when José Antonio was 31 years old. And I'm sure about that because on that occasion, José Antonio was delivering a talk in Paderborn about one of his specialties, namely the applications of spectral analysis to hereditary algebras. The topic you see incorporated in this title, you will see popping up later, now and then. The cooperation I'm going to comment a bit later. So first, my excuse. I've checked that one can find 146 paper of José Antonio, at least in the Mathsinet, so there should be certain more. Already those cover a really huge range of subjects, completely impossible to squeeze this into a 50-minute talk. And so what I decided just up front was to speak only about joint work. And so we have 7 joint papers, and I will speak about 5 of them in different degree of explicitness. So formally, our cooperation started, as you can see, in 2001. In the end of 2000, I got an invitation letter from José Antonio to come here for a longer stay. and this day marks the initial beginning of a long-standing operation and cooperation. So our first project was to deal with wild canonical algebras. So first of all, I remember canonical algebras were invented by Klaus Ringel. They have been in detail studied for the so-called domestic and the tubular ones. In these studies, nothing was known about the wild case, and this was a task we undertook. It took us quite a while from 1991 to 1994 to produce a paper, and then it took another long time to get this paper published. So it was submitted in 1994 and appeared in 1997. So first of all, to start with, we had a completely different understanding of this animal canonical algebra. José Antonio was thinking of it as a one-point extension of a hereditary star. You start with a star and you add one a new vertex with the proper relation. That is for him a canonical algebra. I never understood how to operate with such an object. For me, a canonical algebra was the endomorphism ring of a tilting bundle consisting of line bundles. There's only one such object up to self-equivalence in the category of coherent sheaves, and so it deserves a special name. Anyhow, you can see from that what was typical for the later cooperation. We had just complementary abilities, and we were joining forces, and then doing this we have been successful. Okay, in this process, each of us learned a lot of each other, and this was not only true for this first project about the wild canonical algebras, it was also characteristic for the other ones. I will not really tell you much about what we proved in this paper. I will only comment on two small aspects which pop up later. First of all, we were able to derive a nice formula for the Coxeter polynomial of a canonical algebra. So what is a Coxeter polynomial? You take the Cartan matrix of a canonical algebra, you form some, if it is called C, you form minus C to the minus 1, C transpose. You form the characteristic polynomial of that matrix, and that is the Coxeter polynomial. We derived a very nice formula for that. You can, oops, what happens to this? Oh, it's hardly visible. It's a product of primitives, and I see just there is one factor x minus 1 square missing, where the primitive terms are just the polynomials you get by dividing x to the n minus 1 to x minus 1. To have such explicit formula for Coxeter polynomials was something new. Before, people have just calculated the roots and had some lists of roots in order to look at these things. The manipulation with such formula made life much easier. Another thing is, which is a bit hidden in that paper, an existence theorem for non-zero morphisms, which is reminiscent of the Riemann Off Theorem of complex analysis. So for a compact Riemann surface of genus G, the Riemann Off theorem states that if you take two vector bundles, say E and F, both non-zero, and if you take the Euler product of E and F, and you normalize by the product of the ranks of the two vector bundles, then you get a very nice expression. One has only to do with the underlying Riemann surface. This is the term 1 minus the genus, and the rest has only to do with the two vector bundles, namely the difference in slopes. What is a slope? You have two canonical linear forms on the category of coherent sheaves. One is the rank, and the other is the degree, and this slope is just the quotient of degree and rank. And if you look at this formula, you see that if this right-hand side of the formula is greater 0, which happens if and only if this inequality difference of the slope is greater than genus minus 1 is satisfied, that you get non-zero homomorphisms. And such a result we were able to establish for any weighted projective line. We had to do some embellishment with the formula. With this inequality, we had to add information about the weights. This is the least common multiple of the weight sequence of the weighted projective line, and we had to come up with an additional factor 2. Otherwise, this formula would be more or less the same as this consequence here. The proof of this was rather hard because at that time we used a device which is now quite popular, namely to use stability structure and the Haber-Riemann filtration and things like that. We did this in that paper and came up with this result. The next joint paper, also this took some time to be published between the production and publication date are 3 years. We were dealing with algebras having a tubular family. Here I will be a little untechnical. First of all, I'm going to define what should be a concealed canonical algebra. We did this in that paper more general than it was used in those days. So we are not working over an algebraically closed field. We take an arbitrary Artin algebra. We take a separating. We call an algebra concealed canonical if there exists a tilting bundle on a weighted projective line, or what I've formulated here, on a generalization thereof, where I'm a bit unprecise what this should mean. If we have such a tilting object where A is the endomorphism ring. In this case, it is a trivial consequence that A has a separating tubular family consisting of stable standard tubes. And this separating tubular family, in this case, consists of all indecomposable modules of rank 0. Prime examples for such concealed canonical algebras are the canonical algebras themselves, but also what Ringel has baptized tame concealed algebras. Also tubular algebras belong to that class. There was a long-standing conjecture that exactly for the concealed canonical algebras we can have such separating tubular families, and indeed this is the case. In this paper, José Antonio and I proved the following theorem. If we are starting with a connected Artin algebra, it is concealed canonical if and only if it has a separating tubular family consisting of stable tubes. The one direction is already dealt with by the remark I made before, that if you represent such an algebra as the endomorphism ring of a tilting bundle, then there results a module category that has this separation property. The sticky point is to do the converse, to start with an Artin algebra which has a separating tubular family, then from somewhere, from nowhere, you have to construct a hereditary Noetherian category with their duality, which serves as the replacement for the category of coherent sheaves on a weighted projective line. Having a nice object with endomorphism ring is a given algebra, and I'm just going to mention how we did this. Just from the assumptions, we start with a trisection of the module category. The middle is this separating tubular family. M plus are those modules which lie to the left-hand side. M minus are the modules, are collecting the modules which lie behind. We are ignoring this bad part M minus. We are looking at the union of the first two, and with a proper notion of closure in the bounded derived category, we design this hereditary abelian category. The central point there is that to each point, what means point in this context, if we have a tubular family, we just take one tube. Each tube is responsible for the existence of an auto-equivalence of the derived category, which is basically keeping the tube stable but shifting the rest of the world, and these point shifts are used in order to construct this category. Okay, a nice object falling in the range of ideas which are similar is our paper on the supercanonical algebras. So that was finished in 2004, was published in the same year. The reason was we devoted it to Idun Reiten, and then the publisher was forced to publish it soon. Anyhow, this paper is what I wrote there. A nice paper about a naturally looking extension of canonical algebra. So what did we do? We start with a canonical algebra. We have a starting point and end point, linear arms connecting these two. And some of these linear arms we are replacing by something which is a little bit more complicated, not a linearly ordered poset, but some finite poset that is inserted. We keep the canonical relations, and so we have in this way a construction for algebras which have somehow popped up tubular family. The original one which you have for any canonical algebra, but at a finite number of places you have made something more fancy out of it. So we had very high expectations on that construction, gave a detailed analysis of various aspects. We were not clever enough to figure out what in general the bounded derived category would look like, because that is a problem having too many influence states. The general resonance for this paper was rather poor, I have to admit. So compared to the other papers we have written, this was a flop. So this happens in mathematics. Yes, you start with something with high expectations, and then it doesn't really work out. So we had to do something more simple-minded And that leads me to the topic extended canonical algebras and Fuchsian singularities. So first I have to admit I belong to this species of human beings being collectors. So some people collect stamps, others collect paintings. I collected finite dimensional algebras with a periodic Coxeter transformation. And like any collector, you will have possibly some highlighted points. So maybe once or twice in your life you hit on really a gold mine with the collection. And this is what happened here. So the concept itself is much simpler than the concept we discussed before, that with the supercanonical algebra. That was too complicated. This concept is simpler. You start with something where I have shown here on the left-hand side a copy. This is a prototype of a wild canonical algebra. It has type 4, 4, 4, 4 arrows, and another 4 arrows. And this is the relation, the single relation you have for canonical algebras with 3 arms. What we do is we just add one vertex. Keep the relations, but don't introduce new relations. Doesn't, by the way, so much matter where we add this vertex, if this is here or there or there, whether it doesn't matter whether the direction of the arrow is from left to right or from right to left. All these algebras turn out to be derived equivalent. So if we think in derived equivalence classes, there is just one such an extension. And here we hit the gold mine. In order to formulate this, I have to recall some definitions. What is a Fuchsian singularity? So if you meet somebody from complex analysis, that person will tell you, oh yes, what you do is you consider meromorphic functions on the upper half plane, and you have a discrete group operating there, and you look at something which is more or less the invariant theory of this group action. So there's a special name for this. These things are called rings of automorphic forms. So for people from complex analysis, a Fuchsian singularity is something associated to some discrete group acting on the upper half plane, and these Fuchsian singularities we are able to write down in a purely algebraic fashion, and this is what I did here. So I take the weighted projective line which corresponds to this wild canonical algebra. Then I take the structure sheaf, I take the Außer-Reiten translation of this weighted projective line, and then I form the algebra with n-dimensional graded pieces are just the homomorphism from O to tau to the n of O. This is a nice commutative algebra, finitely generated, and is exactly what people in complex analysis are looking at. So, these extended canonical algebras, just to okay, here's an example. For this example with 4 weights, we get even a hypersurface algebra, meaning it has 3 generators and is having a single relation. This single relation in technical terms, is an isolated hypersurface singularity. And actually, it's the Fuchsian singularity of type 444. So our observation was there are exactly 14 wilds where the Fuchsian singularity is hypersurface. So that means it is given by, of the form, a polynomial ring in 3 variables, you factor out just a single equation. All the other Fuchsian singularities are just what one calls graded Gorenstein. But only few of them are reaching the even next level of being complete intersections. They coincide with the hypersurfaces from something that is appearing in mirror symmetry, that is Arnold's strange duality list. I will show you this list later. And in these 14 cases, that was my collector's aspect, we have algebras, extended canonical algebras, having a periodic Coxeter transformation. And it's basically the only ones, if one restricts to Fuchsian singularities with 3 weights. Okay, here is Arnold's list. Arnold is one of the initiators of singularity theory. He did this work in the beginning of the 1970s. Arnold had 2 clever students. One has the name Dolgachev. You see this name there with the Dolgachev numbers. The other Gabrielov, the Gabrielov numbers. So he gave these students a task to calculate some number triples associated to the singularities where you see the defining polynomials here. So the singularity itself is, as before, the factoring polynomial ring in 3 variables divided by this polynomial. These 2 people worked with different methods, and they came up with different numbering schemes, but if you look closely, every number you find on the left side with the Dolgachev numbers, you find also under the Gabrielov numbers. It's trivial for the first entry. What happens with the second? 238. 238 you also see here. And then you see a pairing of 2 number triples, 238, 245. And in the converse way, you see it here. Just to make a long story short, what people observed was you get the same numbers, but the numbers are ordered in a different way, and there was the suspicion that there was a deep mathematical reason for this renumbering scheme occurring. And so this was running for many years about as Arnold's strange duality list, and this list got talks at the Bourbaki seminar and so on and so on. Only more recently, in the last decades, it has been revealed what the real reason behind is, that there is some mirror theoretic context, and Ebeling and Takahashi have given even a purely algebraic version of this mirror symmetry. So for this talk, all this doesn't matter. I just told this for background. What matters is we found periodic Coxeter transformations. We found these periodic Coxeter transformations in some known and mysterious mathematical setting. Even the periods of the Coxeter transformation, these numbers came already up in this Arnold list as the degrees of the quasi-homogeneous singularities you have here. So that means we found for the weight sequences, the Dolgardchev numbers, if we would pass to the extended canonical algebras, we would find periodic Coxeter transformations exactly of this periodicity. So our task was to give an explanation for that. So José Antonio were working first, of course, on understanding what is happening with the representation theory of the extended canonical algebras. So we were clarifying many aspects, deriving a formula for Coxeter polynomials, deriving consequences for that, namely that only very few have a chance to have spectral radius 1, and then a fortiori to come from hypersurfaces. We derived a complete list for spectral radius 1. We did write down nice properties for the Poincaré series for the associated Fuchsian singularities, and we did really an extensive research and wrote a very nice preliminary paper, which we did not submit because what was our aim at that time was to find a triangulated category of geometric origin which was dealing with these extended canonical algebras. For the canonical algebras, all this was known. But for the extended canonical algebras, we didn't have those triangulated categories of a geometric origin. In order to find this, we had to travel to Madrid. So we both were attending the ICM in Madrid, and it's nice that Bernhard is here. Bernhard gave a nice talk in the algebra section, and after his talk, José Antonio and I were standing together with Bernhard, congratulating him for this beautiful achievement. And then some Japanese colleague was approaching us, not us, was approaching Bernhard, exchanging a few words with him. What José Antonio and I could just overhear was singularity category and Orloff theorem. By the way, Orloff theorem was just put into the archive 1 year before. José Antonio and I were completely unaware of it. We also were not aware about this concept of a singularity category, but it came to us as a flash. This was exactly the object we were looking at. We would take the Fuchsian singularity and look at the singularity categories. And we had immediately our theorem. Just from this conversation. Here I read it, take Fuchsian singularity associated to wide-weight sequence, P1 up to Pt. Then the singularity category of R is triangulated and has a tilting object realizing the extended canonical algebra associated to that weight sequence. Okay, so we had the theorem, but we had no proof. We even had first to acquire knowledge about what a singularity category is. But when we had mastered this, it was a routine thing to prove the theorem. And we are writing now August 2006. In November 2006, the paper was put into the archive. And then it was the publication process was taking some time. So, the last of our joint papers I'm touching on now is the spectral analysis of finite dimensional algebras and singularities. You remember this first slide about this talk of José Antonio in Paderborn in 1989. This was relating spectral theory and the representation theory of finite dimensional algebras. It is a subject José Antonio and later I were not really getting a distance of. So we were always returning from time to time to such problems. Just as a starter, you can, for instance, look at such nice pictures, the snowflake tree, which has n leaves of type d4 tilde and calculates the Coxeter polynomial, and then derive information from that. This is only thought as a starter. There are more serious applications, as you will see now. I'm not trying to cover all the things we did there together. Determining the Coxeter polynomials of supercanonical algebras. You remember this flop business. The Coxeter polynomials of extended canonical algebras will just something I will remember here, because this is one of our secret weapons which has not really taken on board by so many people. I've just write down the context. Suppose we have the following setting. Start with a finite dimensional algebra or finite global dimension, and assume you have an exceptional A module. Exceptional, I recall, absence of self-extensions and trivial endomorphism ring. In that case, for an exceptional module, one knows that the perpendicular category formed in the derived category is a nice thing, and we assume additionally as itself of the form bounded derived category of some algebra. So in this setup we have the following theorem. The Coxeter polynomials for these three algebras we now have: the one-point extension algebra of A with this exceptional module, the algebra A we started with, and the algebra B, the smaller thing for the perpendicular category, and the Poincaré series of the exceptional module, which comes in this format. We have the Euler form in the derived category of A modules. The tau is the also-Norwegian translation in the derived category of A. And then this is the Poincaré series. This Poincaré series is basically derivable from the quotient of the Coxeter polynomials of A and B. This is one of the reasons that Coxeter polynomials have really an impact in the rest of mathematics. And the Coxeter polynomial of the one-point extension is derivable from the initial data by this nice formula. So only to say that there is a real big range of applications, but as far as methods are concerned, there are not really many general methods. One of the general methods is this one. So I'm finishing with this, and I come now to speak about José Antonio personally. So I try to put José Antonio into some scheme. If you look at mathematicians, you will always find 90% of them are very critical about all aspects of administration. So first of all, they don't like to do it themselves. Secondly, if they do it not nicely. And thirdly, they hate any type of political involvement. This is different with José Antonio. I would express it the following way. José Antonio has a political gene. So he is really a political-minded person. He wants to bring his country to a better future. He knows the mechanisms which are necessary to do that, namely to understand politicians. Why do you have to understand politicians? Politicians are the people making the decisions. If you want to change the world, you have to influence decisions. And he knows how they think, and he knows how to influence them. So I list a really impressive number of involvements of him. He was starting very young. This invitation letter I have showed you in the beginning, he was writing already as a director of the Mathematical Institute. He was a long-term director here. He did make many improvements. This is something, some involvement, the second tier, which is not so much known. He was really very seriously involved in the creation of this Universum, this science institute concerning the mathematical branch. So most of the non-trivial exponents go back to ideas that José Antonio was launching. I remember that because during one longer stay in Paderborn, he was still on a daily basis involved, communicating with his partners in creating this institute. He was president of the Mexican Academy of Sciences. He was for many years the scientific #1 at CONACYT. That was a place where it is steered, where the research money gets to. And in such a position, one had a lot of power to influence development. He was a long-term director of CIMAT in Guanajuato. And finally, despite his handicap with the Parkinson disease, he was still initiating new institutes and corporations, for instance, in Yucatan. In particular, there is a mathematical setup in Mérida, where he was the initiator. Also, I still have time. Also, there are many, many meetings he is responsible for. I list first meetings happening in Mexico. So there were 2 ICRAs where he was involved. Pátzcuaro I was putting in brackets because that part was responded as it was under the responsibility of the Morelia Institute. This doesn't work properly. As he was organizing together with Bernhard Keller, Andrzej Skowronski and myself, a conference under the SIMPRA UNESCO umbrella at Tehran. As a spring-off, we now have a mathematical branch of the IPM, the Institute, the Tehran Institute of Mathematics and Mathematical Physics in Isfahan, where Javad Asaduyai is responsible for. In brief, the SIMPA conference brought representation theory to Iran. So here are now some meetings at Banff and continuing in Oaxaca, where I have listed the names of the organizers. This meeting in Banff 2012 was, no, I don't see where the spectral problems are. Most probably I've forgotten one more meeting on this slide. Shaping the future. In Mexico City, during his rectorship, he was in charge for starting the enlargement of the Mathematical Institute. In Guanajuato, most people here have been there and seen this new complex that has been built there. In Merida, in the framework of this Yucatan initiative, he did a lot. And last but not least, he was in charge creating a Mexican branch of this Banff Institute, and for the start of this in Oaxaca. So that is the end of my talk. I am sure you will all join in the congratulations for the achievements of José Antonio. And happy birthday. It was a pleasure.